Hi, Marko.
Hi, Sherry. How are you?
All right, and you?
Yeah, good.
Excellent. Sorry about the delay. I had two meetings on the go, and I needed to end the one meeting so that I could transfer the control of the other meeting to that device, so I could start this one. Yeah.
Okay. Am I allowed to share the screen?
Okay.
Just test that it works.
Yes. I'm seeing your desktop.
Okay, and if I go to presenter mode.
Perfect. I can see your.
So you can see the title page. You're not seeing any.
No, you're not seeing any other.
Yep. Okay. Perfect.
That's perfect.
I'll get out of that and I'll stop sharing. Great.
I'm looking forward to this.
I'm terrified. Anyway.
It'll be fine.
Yeah, no, it's good. Do you know who's joining?
So it's the usual GCC mailing list that I send it out to. A large portion of research groups, and then we've got some industry professionals that we invite along. We do have some guys who join us from Canada, but because it's like 3 o'clock in the morning there, I usually just send them the recording link.
Okay. Yep.
Otherwise, they have to get up very early. So yeah, people from all over the world. I usually have between 30 and 50 people joining.
Okay.
And we're in the process of trying to bolster the mailing list to get more invites going out.
Okay.
But it's a large portion of researchers.
Yep. Not too many industry people there.
Some.
Recording. Okay.
Okay. So while we are still waiting for a few people to come in, just let me say it's a pleasure to really have Marko today here. Marko has been already nominated a member of the GCC earlier this year, so it was a great pleasure for us to have him on board. Marko, of course, has been very early on in the very early days of the GCC, isn't it? Over 10 years ago, engaged with us, engaged with all the initial studies we did with Anglo, so back in Mahalaquena. Very good memories from that, Marko and the group. So it's a great opportunity we have here today to hear you. So please, Malcolm, maybe you can go ahead and introduce Marko, but it's a great pleasure to have you.
Yes, very good to have Marko on board and one of our new GCC members. And you always have to be cautious when you ask Malcolm to give an introduction, because you never get a formal, regular one, I'm afraid, Marko. So my understanding of Marko's history is studied mineral processing at UQ, went off and worked on site in West Australia for, no, you didn't study at UQ, it was, where did you study your mineral processing, Marko? I know I've just
that wasn't UQ.
Was, okay, no, I've got you mixed up. And then you were site mate for about 10 years, did real work, learned how to take samples and things and run plants.
Only 7, yeah.
7, I knew I'd get it all wrong, okay. And then came to the JK, got rid of the site work, came to the JK, so his wife could earn the serious money and he could just be a researcher. And I think that part's accurate. And did a PhD in screening, dabbled a bit with looking at DEM, but actually got down to using the principles of similitude, which Marko still applies. And I think where Marko's real strength is insights into process. So we're on site, Marko's fantastic, and sitting there quietly and then absorbing how a process runs and thinking about how you use that understanding to change the process or to model it. So I think he's a great teacher for us of how to think deeply about a process and learn from it, not just read about it in a book and copy some equations down. So Marko's a great one for having extended discussions about what we really think is happening. Doesn't just accept someone else's view, which is great, which is what a researcher should be doing. Dion Weatherly, who you might know, Marko, share an office, and they have quite different approaches to life, shall we say. So there's a lot of dueling across the office, which has been fantastic from a perspective of pushing each other's boundaries, which again is what we should really do. And I'd call Marko our quiet powerhouse, not one at the front being noisy in front of the stage, but except for today, it really has done a whole range of stuff from mill models, power models. This liberation work he's going to present today, did in his garage at night, I think, and we managed to get some funding in, but did it because it was interesting and he could figure out a novel way of approaching it. So I'd say great to do modeling work with and be on site with, and a fantastic traveling companion, which I'll only describe offline. So Marko, over to you. Look forward to your presenting to us your view on liberation of minerals, the Mineral Association. So you can take on the screen.
Yeah, thanks very much for your intro. I'll share the screen. Is there something there?
There is.
Is there a title there?
There's a presentation.
Perfect. Okay. So, yeah, first of all, yeah, I'd like to thank the GCC leadership for asking me to present, and to all of you for taking the time to participate. Today, I'll talk about a model I've been working on and off over the last 10, 11 years. And I suspect a lot of you seen this work presented earlier, but so apologies in advance if you find there hasn't been a lot of technical progress since then. But even so, I'm really keen to see the conversation about modelling liberation going, and hope to have plenty of time for a good discussion at the end as well. So here you can see some quotes of some, I think, important papers on liberation modelling, and many of the researchers in this field warn that modelling liberation is a difficult problem. They use words like a geometrical problem of considerable complexity, that it's one of the most difficult conceptual mathematical problems in our discipline, that there's no adequate model of liberation, even for binary systems, for modelling mills. Maybe that's changed since then. And that it's a very difficult subject. This word difficult keeps cropping up. But despite this, it's also a very important problem for the whole discipline to be working on. And developing a model that works for all ores is obviously something that we need to work towards. But we need to have realistic expectations as well about how to model this process, because it is so complex. So there have been a lot of attempts to model liberation. There's plenty of models out there. A popular method, and one that I've followed as well, is to define a 3D geometry that represents the unbroken ore texture. And Godin's model is considered to be the first of this type of model. And it's just a simple grid of uniform grain sizes. But this turns out to be way too simplistic in practice. Weigel improved on this by randomizing the grain positions, though still with a uniform grain size for both phases, but it isn't much better accuracy-wise. But both Godin's and Weigel's GRLM have analytic solutions, so that's a positive. But more recently, there's been a number of voxel-based models that have been developed. So Gay using spheres, Vasiliev using Voronoi, Wetzel and Andrusevich using micro CT textures or rectangular prisms. So this is an intuitive way of modeling, but in the simulated textures are often just too simple to represent a real ore. And a problem with these voxel-based models is that the voxels are indivisible, and it's not possible to make a root 2 series of particles using integer voxels. So you tend to have a trade-off between resolution, that is the number of voxels, and simulation speed. So on this large one here, 5,000 voxels on a side, that works out to, if each voxel is 1 byte of memory, it turns out to 125 gigabytes. And that's clearly a very large memory structure to process it even on very good computers. So the simulation speed is actually very slow. You can simulate a smaller model, but it's then has less resolution, so that you have this trade-off between these modeling approaches. Another popular modeling method is to use 2D images of the intact texture and to overlay a tessellation or fragmentation mask, which defines the particles. So simple shapes like circles or squares have been used, but a lot of the recent work uses Voronoi tessellations. And an advantage of this approach is it has the potential to be extended to non-random breakage as well. Also, the method is well suited to core scan data and studying coarse liberation. But again, each tessellation makes only a relatively small number of particles. And if you have to repeatedly make particles to get good enough statistics, it's still fairly slow. And it is a 2D approach. But it does have its place as well. Another modeling approach is using DEM or FEM, and these can be used to simulate fractures and create particles. The advantage here is the potential to simulate realistic non-random breakage in either 2D or 3D. But again, it's extremely slow, and each simulation can only contain a small number of grains and a relatively small number of fragment particles. So you'd need a large number of particle simulation breakage events to get statistical accuracy. There are some brilliant theoretical models as well. And an important one is by King. And as I understand it, it incorporates a lot of the work by Barbary and others. It starts by measuring intercept lengths, so using automated mineralogy. So back in the day, they used to do linear scans rather than area scans, using their electron microscopy, and a lot of complex maths, including stereological correction using a software called Pargen, finally gets you to a liberation spectrum. And it has been extended to include non-random breakage, but it is, at least to me, a complex way of calculating things, and it does work only for binary systems and ternary systems in some special cases. So this is an approach that has also been used, but it's a bit scary for me. Now, liberation measurement has come a long way, and the work of Purdy and Sergio has developed a means of balancing liberation data around a circuit. And this is certainly a good option for modeling liberation if you have the luxury of having this depth of data. So the original vision or research question I had in mind for my research was, can we extend Godin's idea to multi-mineral textures? And can we incorporate comprehensive analysis similar to MLA or QuemScan and particle-based separations? So when we're developing a model of something complex, we often develop a mathematical abstraction, which could be defined as the process of taking away or removing characteristics of something in order to reduce it to a set of essential characteristics. So, for example, if we're modeling the gravitational force acting on a cow, we can consider a spherical cow. To tackle the problem of multi-phase liberation, if we use, for example, the texture on the left, we can create a simple analog of this by replacing the grains with a square shape, and it would still have many of the textural features of the real texture, but with the exception of the grain shape and grain orientation. And if it turns out that the shape has a dramatic impact on liberation, then this obviously would be a poor model. If it doesn't, this abstraction would allow us to describe texture with a computationally efficient data structure. So the model I've developed makes a 3D model of a texture using just simple parameters. Firstly, the modal mineralogy, i.e. the grade. So if we have a 5-phase texture, which we've simplified from this image, there's basically 4 degrees of freedom, and grade can be measured or estimated. Then there's the grade grain size distribution. So there are several 2-parameter PSD models, and Rosen-Ramler, for example, is as good as any. So for 4 mineral phases, that's another 8 parameters, which also can be measured or estimated. And if you look at the image, you can see that the biotite forms a halo or rim around the olivine minerals. So it appears that we can add a parameter that specifies the proportion of biotite that appears in that form as well. So we don't need to define the grain size distribution for that because it's just wrapped around the olivine. So 13 parameters describes this model of the texture and gives a 3D, and you can see the 2D slice there as well, which is a representation of the measured texture. So the geometrical texture or liberation model offers a way to create textures that represents an intact or parent particle. And the model algorithm converts these model parameters into grain positions. And alternatively, we could have measured the texture using tomography and created a model, but I haven't done that to date. But and in this example, I've just emphasized the spatial clustering. So some of the minerals are sort of clustered in this texture. And this property is important because you see this in real minerals where you have veining or parts of the rock being almost barren of mineral. And once we have this intact texture, we can then sample it to create virtual particles. So if we select a random point, we can calculate all the grains that intersect with a particle generated at that point. This is sampling with replacement, so we can make as many particles as we like of as many size classes as we like. To be clear, the grains in the model and the particles created are not based on voxels. So they're defined by a center point and size, which is basically 4 double precision numbers. And therefore, to calculate a particle, it's necessary to calculate the intersection volumes and areas with all the other grains. And from this, we can calculate the composition of the particle. These equations are known for orthogonal cubes and spheres. So therefore, that's the shapes that the model uses. And this mode of calculation is what makes the geometric texture model much faster than voxel-based models and permits simulation across a wide range of particle sizes, as well as the ability to simulate low-grade ores. I'll talk a bit more about that later as well. Another unique feature of the model is that it can model grains inside grains. So there are what I call primary grains that are surrounded by the matrix mineral, as shown on the left, but secondary grains that are inclusions within the primary grains, as shown on the right-hand side. The model can also control the spatial distribution of the secondary grains. So secondary grains can either be rimmed around a primary mineral, randomly distributed within the primary grains, or biased either to the center or edges of the primary grains. And you can have multiple secondary grains in a given mineral as well. So these tables, or locking and association tables, show the proportion of each type of particle. So you can see the particles that are liberated, are binary, and with which mineral, and the ternaries, complex, and all of these add up to 100%. And you can see that if you have just primary grains, the type of binaries that you create are just the colors with the matrix mineral. Whereas if you have secondary minerals, you can get binaries between these different colors. So, and fewer of these others. So the association basically controls the kind of binaries that you produce. And you can imagine that if you took a sample of crushed ore, analyzed, created these sort of tables, you can begin to infer the intact structure of the ore just from the particles, basically putting the ore back together again. So I'll talk more about that a bit later. One of the model outputs is a large table that contains properties of, or actually series of large tables that contain properties of each particle created. So if you're creating 10,000 particles per size class, there's a lot of information there. So for each particle, you can calculate the density of each particle and then its composition by volume, by surface area, by 2D cross-section, by perimeter, by line. And this information might be useful in different contexts. As mentioned before, produces these association tables and in 3D, 2D, and 2.5D as well for different sizes, just showing a small number here. But you can see that at a coarse size, most of the particles are, in this case, are ternary. As you get finer and finer, they become more and more liberated, and the ternary particles become fewer and fewer. Another model output is some plots. So basically you can create liberation distributions for the 2D, 3D, and so on. Locking distributions, so the so the liberated, binary, and ternary particles, and also liberation by class, by size, density by size, and I mentioned before, the model can simulate cubes or spheres. And actually, the effect of the shape turns out to be not very much at all. So you basically get very similar liberation distributions from these shapes. So I tend to suspect that the effect of shape, especially when you have a wide particle size range, is sort of overrated, really. And here's just another example. Again, the simulations show that there's not really a difference between the cubes or spheres. So I tend to go with the cubes most of the time because it's a faster calculation. And maybe a comment on sampling statistics though, because this is a stochastic simulation. So you are sampling the texture many times, and the more you sample, the smoother these distributions become. So if you were to sample just 200 particles per size class, you'd get a really wavy distribution. As you sample more, you get a smoother distribution, but the simulation time also goes up. So I typically go for around 10,000 particle size per size class for a relatively high grade texture. This is with 40,000 grains, by the way, in this texture. Now, if I went to a much lower grade texture, and this has a very low grade, this is 50 parts per million for one of the phases, and 550 parts per million for the other phase. You can see that 10,000 particles per size class doesn't cut it. You have to go to a higher number of particles, but that increases its simulation time. But the point is that you can actually do those you can do liberation calculations even with very low grades. So far I've talked about artificial textures, but it's also possible to fit parameters to match the data from automated mineralogy. And here I've backfitted parameters to some data from David Bajewski's excellent thesis using George Fisher-Orr. And basically, again, using these tables, the simulated and measured quantities are fairly close once the model parameters have been calibrated. So using this approach, we can backfit that texture just based on liberation data. So the fitted model of the texture contains a band of gangue mineral on the right and a band of pyrite-rich material as well, which doesn't contain much of the sphalerite, the pink mineral grains. And the texture is extremely fine. So this texture represents basically it's a representative or archetypal texture that's useful for modeling. It's not like a rock, just a rock handpicked off the stockpile, which can vary in composition and might not be representative of the ore. it's because it's been backfitted from a ground ore, it's representative of that stream. So an important feature that I wanted in this model is to be able to do particle-based separation. So a conventional approach to modeling might be to take a intact texture, break it into particles, calculate the liberation at each size fraction, and create, for example, a density distribution, and then feed that to a separation model somehow and get bin data out. The problem with this is you lose information if you bin the data. So each bin has a specified property or a range of properties. So you lose a little bit of information in this process. Instead, what I want to do is, as I break into particles, I want to feed these particles individually into a separation function. So that function could be very simple. For example, is the density more than 3.5? Yes, no. And you can separate the particles and no information has been lost yet at that point. So in particular, when you have complex separations that rely on several ore properties, it's much better to do it this way. If you have a liberation distribution that has that relies on one property such as density, and you need a model that can, for example, consider surface composition, that's going to be a problem. So, another output of the model is to create these similar looking tables also for the separation products. So you have sinks and floats for this density separation. You can calculate the mineralogy of the liberation of the separation products, as well as the by size, calculating the average grade and mass recovery to sinks, for example. Now, I've dabbled a bit with a simple particle-based flotation model, and basically it's just an elephant curve, two back-to-back S functions, and fitted this to a set of data from Whiteman. This was actually on a nickel ore, but basically shows the recovery as a function of particle size as well as composition. And what I want to do is to simply apply this model to the Bojevsky data as well. So with the fitted feed texture, I wanted to see if I could predict the final concentrate properties. So the assumptions were that you just using the texture from the feed particles only, using the measured grind size to give the proportion of each size class going to the separation model, and then assuming that the sphalerite floats as per the flotation probability model, and all of the other minerals recovered purely due to their association with the sphalerite, and comparing the experimental from Bajewski's work with the simulated results, you can see it's not perfect, but it's actually not too bad. So it is a reasonably predictive way of estimating what you might get from an ore without actually doing any experimentation. So there's no fitting parameters here at all. And also looking at the liberation, the liberated binaries and ternaries, again, quite similar to the measured numbers from Bajewski. So overall, it does a reasonable job. I need to do this for more ore types, I guess. And basically it comes to the limitations, I guess, and where I see this model is needs to go, I guess. And one of the big limitations, as I said, is that even though I feel the model's come a fair way, there's a lot left to be done, and getting the model so that it can be used by others is one of the things that I'm really conscious of, and also developing new capability for the model. For example, being able to simulate non-random breakage, because at the moment the breakage is random only. Also, the current method of model calibration is fairly clunky. So developing better ways of automating that process is something that I've been thinking about as well. A really difficult problem is to simulate recycle or rebreakage so that it can be used in mill modelling. That's something that the model can't do at the moment, and needs a lot of research to figure out how to do that. Also, as I alluded, being able to simulate, create the textures from tomography textures. Also, validation, testing, adding new features. So there's really a lot of work that needs to be done to continue this and get it where it needs to be, I guess. So with that, thank you. I'm hoping we've got plenty of time for questions.
Just keep my screen up. So as usual, a really clear and succinct presentation from Marko. So I hope that's grabbed some people's imagination as to what you might be able to do with a model of that sort. And note that Marko said you can simulate different forms of the particles, and that's what really gives the strength to backfitting the model, because it could be planar like an SEM micrograph. You don't have to do any corrections. You actually use the planes. It can be volumetric, so by density, it can be what you see on a surface. Extremely powerful. So we really, maybe this is one of the pathways to start getting this out there, other than just in some publications that haven't hit the world headlines yet. So we've got some interesting questions out there, I'm sure. And shove up your hand or just button. Yeah, see David's there, great.
Yeah, look, amazing work, Marko. I mean, the thought of being able to simulate the textures, and something we've been grappling with at Newcrest for years, is we're seeing textures, we're seeing when we scan core, we're seeing textures, we know it's driving recovery, and we're trying to understand it. And I think, you know, one of the most recent things our mineralogists, who are probably a couple of rooms away from you, are finding, particularly with Cadia, is they're looking at just the amount of grains, the percentage of grains less than a certain number. At the moment, I think for Cadia, it's 6 micron. For Red Chris, I think it's 3 micron. And they can plot a line of that versus recovery. So we're starting to be able to see that, I think, see that link numerically. And sorry, this is probably more of a comment, but certainly an offer there that we have a heap of data. If you want to play with some data, the guys there have been collecting not just MLA data, but also micro XRF data, which is going to a slightly larger scale. And maybe it's a relevant scale. We're not entirely sure, but they are seeing, when they look at this micro XRF data, they're starting to see kind of visual connections between what they see in the texture and the performance they're seeing out of the geomet test work. So certainly happy to open that up and put you in touch with a few people there to have a look and see if it's of any use.
Yeah, thanks for that, David. So yeah, the data needed in particular to backfit the model is liberation data at multiple size fractions. So if you have that, I'm certainly very keen.
Yeah, look, let's take it offline. We can certainly have a chat, and I'll put you in touch with the mineralogists at the JK, and you can ask, you can talk to them in a lot more detail. But yeah, there's a heap out there. I don't want to take all your time here. Just interested in your thoughts on that next step of trying to move away from the non-random breakage. I think breakage is non-random from everything we've seen.
Yeah.
And what are your thoughts on how to take that next step?
So what I've tried to do is incorporate non-randomness in the texture itself. So that's one step, but it's definitely the case that you can have grain boundary breakage, or you can have different mineral phases that are softer or harder than others, and it will cause non-random breakage. It does. What I've tried to do is to create a model that's fairly simple. And adding that non-randomness is makes the model much less simple. But there may be ways of emulating that breakage behavior. I've got some ideas, I guess, that I'm still working on. But yeah.
Yeah, I think it comes across that start with a non-random in any ore, and then see how close you get and decide whether you really need the random. You get differential breakage as well.
Exactly. Maybe classification's enough to drive it. I guess that was my other thought, is that may well overprint a lot of what we see as the non-randomness.
Yeah, so I think we have a tendency to misinterpret the end product.
Correct. Yep.
Marcelo, you had a question.
Yes. Well, as usual, Marco, fantastic presentation there. I think this is a great approach to liberation. I think the degree of complexity that you got in which is grains within grains association, is just completely out of the ordinary if you compare it to anything that is out in the literature. So really fantastic work. But of course, since we are following David's comment there on the non-random breakage, I just want to just a bit more on that because, for instance, as you know, one system that I'm very keen of because of some work in Brazil is itabirites, which is low-grade iron ore. And in that case, we are pretty much peeling the layers of the onion, I'd say, by understanding how much of the behavior is because of differential breakage of hematited quartz. And we can do that in the lab nicely because we can characterize the different components. And in that particular case, maybe a binary case, we could see that, yes, indeed, differential grain boundary breakage is quite massive because I tried to use your model once and it's really very far because it is so massive that I almost consider like it's perfect separation and deliberation would do. So I was kind of wondering a little bit more on that, and that perhaps using a very simple texture, simple system like just a binary, if you already have your thoughts there, because if you go straight to the very complex system with non-random breakage, I think it's a bit too much because you have too many unknowns there. For instance, differential breakage responses. But maybe a system like a binary, an iron ore, will be the first one to give a kick on this. What your thoughts on that? Another quick question also is that, yes, and definitely I have been thinking about your model for a very long time, but also the rebreakage issue is something that pulls me back in the sense of how we can actually put this into a ball mill model, for instance. And of course, that's a major limitation because it's a texture model to predict from an unbroken material. And in that sense, what do you think about just really doing some brute force approach of modeling, like people like Peter King has done in Andrews mica diagrams, like using this as a virtual experiment where you actually have the unbroken ore breaking into size distributions, 3D size distributions from a known composition, and modeling that using just the functions, and then using that in a ball mill model. Because that may be something like a compromise to use like a brute force rebreakage phenological approach with your way to actually get the fantastic 3D data from breakage of a known particle composition. Well,
difficult questions. Definitely with the non-random breakage, using a simple system is the way to go. I actually started by wanting to model the complicated one. I wanted to model the multi-mineral system. What do you need to model multi-mineral systems properly? And to do that, you really have to have grains inside grains for the reasons that I presented. It just controls the type of binaries that you get. So you have to have that in there. When you have a simple system, and unfortunately in liberation, even simple systems are complicated. It is, of course, it makes things a lot easier. And I don't think even having 4 minerals to do non-random breakage would be possible. We really have to start simple. But yeah, it is a challenge though, because I mean, it's a while since I've had proper funding for this project as well. So it's sort of been on the back burner. I sort of have permission to do a bit of work on it, but yeah, it is something that I've done on the side really. And hopefully some other things do come up in the future. So, I mean, we are working on getting some projects.
Marcelo, your question about the brute force and a mill and a circuit.
Yes.
Mark and I've passed ideas around, but are you saying you just take that closed circuit as a black box and just say final product fresh feed, or you mean something else?
Yeah, and that actually what I thought was actually the idea behind the Andrews mica diagram, which is to, let's say you have a rock that you know the composition and unbroken, and then you break that in your lab under control conditions, and you look at the size distribution, basically do a full MLA of that and model that as a fingerprint of what would be like the self-similar behavior of breakage. So of course that corrupts the idea that Marcos has in his model, but allows to use in a proper rebreakage environment as a breakage function with composition. I was just wondering if what your thoughts about that, because it would be in principle possible to input that into typical ball mill models that consider breakage function.
Yeah, I haven't really thought too hard about combining it with a ball mill model, because I know it's a tough problem. And the way I've conceptualized rebreakage is to take the particles from the separator and then turning those particles individually into a new parent particle and trying to break those, which computationally makes things sort of mental. So again, it's a very difficult problem. Out of that list, that's the one that scares me the most.
But like David, I'll definitely take these offline, because I think that this too can be shortcuts we can talk about later on. But great, thanks, Marco.
Thanks, Marcelo.
And Megan, over to you.
Hi. Right. Hi, Marco, and thank you again for an excellent presentation. And I mean, I know we've talked about this model before, but there's two things. You've never actually told us how long it takes. So if I give you a texture for you to get it to be something that we can use, how long is that going to take? And then we talked about possible textures. And I don't know if you've ever thought of trying to model the UG2, because it's, in my head, it's a simple OR, but when you start talking about the number of components, maybe it isn't. But it definitely has this non-random breakage component with the chromite that is, it's very sugary and spherical, and it breaks very easily from the matrix. But so you've got the chromite that behaves one way and the silicates that don't. But yeah, we wrote a paper with, Aubrey wrote it with us a few years ago about looking at particle shape as an indicator of non-random breakage. So you know, the samples, the QuemScan data, all that still exists. So yeah, maybe if you're also ever looking for more case studies, it's one to think of.
Yeah. Sorry, Megan. In terms of how long it takes, the simulations themselves are quite quick, but creating that texture, that's at the moment I've got a fitting methodology that's it's semi-automated, shall I say, and I know we can do a whole lot better, and of course that process is something that at the moment takes sort of hours, days to do, even though each simulation is reasonably quick, like less than a minute kind of thing. Sometimes well less than a minute. So, but the point is though that at least with this type of approach, it's possible to do a parameterized model. It's possible to fit. If you've got a simulation that takes hours or days to simulate, you can't easily fit a model like that. If each instance of the model takes a day to simulate, for example.
So the fitting process, you're basically running the model and changing the parameters, classic way. So you run it 100,000 times or something to converge, which can take 4 or 5 hours for one convergence. And you've got to spend the time up front to arrange all the data and get it into the system to analyze it, if I understand. So it's like a couple of days,
Yeah.
we've got a new ore till you've
Yeah,
fitted it.
It's a clunky process at the moment. What I basically do is I've got I calculate the sum of squared errors between what the model does and the data, and I've got basically an experimental design, and I create a sort of a multi-dimensional experimental design, run that. So there might be, say, 100 simulations in there, find the local minima, and keep trying, basically. But I know we can do better.
Okay, thank you.
Right, what else do we have out there? Bound to be another hand coming up somewhere. Such a complex and wide open topic, unresolved in my view. I think my completely unbiased view is this is the only working model I've seen like viable to use in a mineral processor. What Mark has laid out is this is in principle hard work, so the big trick of not forming voxels using vectors, and the thing around differential breakage, which means different parts of the ore break into different sizes naturally. I think we can put it by putting a bias function in. So when Marko selects particles for breakage at that point, you could bias the function. Of course, I've had no bright ideas of how to bias that. Just said, Marko, I think we can bias that function. Walked out the room and left him with the problem. But it's the kind of thing I'd like to seed in people's idea and their minds to come back to Marko. How I think we can do it by biasing, because the different components break naturally into different sizes, a bit like you were saying, Megan. You know, that and very much for the ore you were talking about, Marcelo, that they naturally break into different sizes of solution. And that's almost a step towards differential breakage. All my observation of particles breaking is the cracks just go through everything. They don't care. But when they go through different components, the product size is different. So it actually switches as it goes through hard and soft. And that's more the differential breakage rather than, so it's a differential mode of the parts breaking. And that gives you what looks like a bias in your breakage, or a selectivity that's not necessarily there. So, I mean, that's my 10 cents, that maybe that's where we start to see how much of the problem that answers. Anyway.
Yeah, there's a similar approach that I think someone's done it using the 2D tessellation, say, where you have the image and you make the tessellation with the Voronoi. You can bias the seed points depending on the mineral, and that can give you a finer grain size near the in certain regions depending on the mineral grade. So doing something like that might work, but there is a difference, because those tessellations basically turn that map into basically into particles that are touching throughout the texture, whereas what I've done is basically sampled with replacement. So their approach is sampling without replacement. So it does make it difficult to apply that. I could perhaps go to a sampling with without replacement methodology and do that.
In principle, your method is it's an infinite block of ore with this texture, and you're sampling. It's not a particle you're breaking; it's a block, and you've got to have enough resolution there to sample from randomly in all different methods, and you build up lots of particles in each size class. It doesn't predict the size distribution. We do that separately with a breakage test, and then superimpose the sample particles into the size distribution. And they, I think there's a way we can bring those together. When you break differently, you get different size distributions, and with the differential breakage. And I think that's an opportunity that this kind of group and forum could maybe bring those ideas in to use the tool you've got, which is quite amazing, and then bring these other capabilities to bear. Okay, well, we've come neatly into our hour. You've allowed really some quite deep discussion. I think the depth of discussion blew everyone else away. And I think Marko would welcome any follow-up, ideas or samples that could be calibrated and things. And I'm convinced that most of you are not trying to just work on this. Someone's going to come and fund it as well. I'm working on that in the background. So well done, Marko, and well done on just doing it out of your own volition. This is the research between the cracks. No one's seen the pathway to fund it. Marko's just said it's important and it's fun. And he doesn't know what else to do on a Sunday between 10 p.m. and 3 a.m. So this is what he does. So well done, Marko, and thanks for a really sterling seminar. Excellent quality, much appreciated. So well done, and see you guys at the next seminar. Bring some more friends.
Yes.
Everyone, well done, Marko.
Thanks very much, Marko. Well done.
Thanks very much.
Thanks,
Thanks
Marko.
all.
Fantastic.
Bye.
Thank you, Marko.
Okay.